Oh, hello. Okay. Look at results and troubleshooting, look at some common tests, and then we'll also, for the last part, we'll look at my own L2 rocket and do a little rocket assembly. Okay. So, what is the role of testing? By the way, for those of you who don't know, last year I was testing associate lead for NASA USLI, so I have just a little bit of experience testing things. So we start off with a goal, and then our tests and designs kind of influence each other. So before our design, we are going to inform design decisions. So we're going to look at our design and we're going to look at where can things fail. And it's a lot of critical thinking, a lot of figuring out how can things fail? How can we stop them from failing? How can we make sure that they won't fail? And then during design, we're going to verify things. So that's what a lot of testing does, is just verify things. Like you go through the USLI reports, we're going to have giant tables of this is what we want to make sure will happen. This is how we're going to verify that it will happen or that like it won't break or something like that. And this is our proof that it didn't break. So that might be a test or something. Go for it.
In industry, testing is often under the umbrella of systems engineering, where like you said, we start off with a goal, a need. We have like a concept, and we go through. That's where requirements and architecture come in, and we kind of define this, and that's where requirements are where we derive what we need to like verify and test oftentimes, and also with failure modes and effects analysis, which happens early on, and being able to generate tests doing that. And that goes into integration and testing. And it goes all back and forth, just like it is shown up there, because oftentimes you'll have to start over when something goes wrong, and figure out a new and better way. And then you have to verify that that in fact works. So it really is all connected. Requirements is like a foundation of creating like a viable product, or a process, in this case, a rocket. And so verification and validation becomes extremely important in testing. And that's why you'll see a lot of stuff. Integration and test often falls under this umbrella of systems engineering and industry.
And actually, I don't think I picked this up on the mic the first time, but we are joined by our this year's USLI testing lead, Skylar. Okay, so this is a broad overview. So we start off with areas of consideration, look at what parts of the design might be able to fail. And then from there, it gets broken up into the two big categories are the launch vehicle and the payload. For the launch vehicle, those tend to be pretty similar from year to year because, of course, we're building a rocket from year to year. So you can look at different things like strength, function, behavior, and simulation. And then for the payload, that varies a lot more because it changes a lot more from year to year. Like, last year for USLI, we were building basically an RC plane. So the mission goals for that were a lot different from this year, where it's a lot more transmission-based objective with like transmitting sensor suite data. And then you go over to Spaceport, and their mission goal is to record the rocket as it falls. So they have to look into a controllable camera, a tracking system. The payload varies a lot more. And then we got our testing categories. So this is what made me like hit my head into a wall over and over and over in the last year, because for the USLI reports, we had to look at each test and say which one of these it was. And it took me months to actually really understand what the difference between each of these was. So I'll try to explain it the best I can. So a test is defined as a rigorous and systematic method of checking a parameter as a specific criteria for passing or failing. And then you collect data and compare to an expected outcome. So an example is a vibrational resistance test. Another example that I could give is we do materials testing each year. So like uh, last year we wanted to test out the strength of our avionics bay. So we took our subscale avionics bay and strapped it into this machine called an instron, which pulls with like a very specific amount of strain being applied to the object. And we looked at how much strain we had to put into the object into the ab bay before it like totally broke. And from that, we were able to figure out how much stress it was able to take, and from how much stress we were able to figure out how much force it took. And then from that, we were able to see, okay, is this going to survive what we expect the force of the parachute to be on it? Because of course, when the parachutes come out, that puts a lot of force on the av bay. So we wanted to make sure that it's not going to totally like snap in half when the parachutes come out. So we did that test and we were able to see that it looks like it'll be all good. Another one is a demonstration, and that's showcasing performance of a system, and it assumes one successful completion implies future success. So a big one for that is our ejection demonstrations. A little bit before launch, anytime we launch a new vehicle or an updated vehicle, we will put in its ejection charges and we'll put in its parachutes and its shock cords, and we'll just test the ejection to make sure that the parachutes come all the way out, so that when it comes time for launch day, we know that our ejection charges are big enough or everything fits enough that the CO2 canisters can blast it out. So that when it is time for launch day, we know it's going to work. And that's something where we're not really measuring anything. We're just running the demonstration and seeing, okay, did the parachutes come out? Yes or no? If it's yes, then we're good. If it's no, then let's look back at the drawing board. Maybe we need to up the ejection charge size. Maybe we need to pack everything a little tighter, something like that. Then you've got analysis. That's methodic and detailed examination of a system for purposes of explanation or interpretation. So the big things for those are like a simulation or a calculation or a survey. So that could be something like computational fluid dynamics, CFD, or it could be finite element analysis or FEA. Generally, this kind of stuff happens on a computer because it's basically just like a lot of math. You do a lot of math and you see, okay, is it going to work or is it not going to work? And then you kind of go from there. Yeah.
Furthermore, when it comes to analyses, they can take a while, especially with a lot of different software. That's why we're quite lucky. I know that Spaceport now has access to HyperGator.
Really?
Yeah. They announced that recently, so they'll probably be able to get some analyses done a little bit faster than we normally would. I know that sometimes they would be waiting for 2 hours for the boat tail analysis. But another thing that's worth noting is that when it comes to doing analyses, they can also provide support for other tests. So for example, when we're doing certain things like flight simulations, and we figure out like, hey, we expect this amount of force on the vehicle during operation, we can kind of use that as a baseline for the criteria for passing or failing when doing other stuff like materials testing. So they some types of tests, or I guess product verification methods, can be used to support others.
Exactly. Yeah. Analysis. Some of it takes so long. Oh my gosh. CFD can get pretty crazy.
About it, so I was there with Roman
Mhm.
during his meetings, and I was like watching this just go on and on.
Yeah.
As you do.
Yeah. And then we have inspection. Inspection is the examination of a system for criteria to determine a condition or a status of the system. And most of the time, it's like it can be determined by observation. But there are some exceptions. So like, there's like the center of gravity So like every day, or not every day, every launch, we tie a rope around the rocket and we hang it to see where the center of gravity is. And we just double check to make sure that it's like around where we expect and that stability looks good. Um, what I think a great example of inspection is like imagine if you have something like a boiler and it has like a pressure gauge on it. You might go look at that pressure gauge, and if the dial for the pressure is in like the green zone, like lower pressure, um, then that your inspection is passed. Okay, the pressure isn't too high, it's in the green zone, we're all good. Versus if the pressure is like way more than it should be, the like pressure gauge on it goes into that like red zone, and then like okay, we got to take a look at this thing. So most of the time it is an observation, but there are some exceptions to everything. Okay, so next up is a testing plan. A lot of times this is also called a testing campaign. So there's a bunch of different steps to this. We'll start off with identify. So that starts with your design goal. So that could be the requirements from your competition. It could be just what you want to do. Like between our two teams, the NASA USLI team has a lot more requirements than the spaceport team. So there are different things to weigh in for that. And you got to look at what do you want your design to do. Go for it.
So another thing is that I suppose relating this to industry, you'll get customer needs for a product or some other process or something. And you can't really do much with those until they're like translated into engineering terms. And that's basically the purpose of like transitioning customer needs to sort of quantitative requirements that we can continue to create testing procedures for. So there is like bridging that gap between customers and the engineers who will be working on the product. So yeah.
It's and then we've also got we got to look at our potential failure modes. Just like when we were comparing design and tests, we got to figure out what can fail. How are we going to make sure it won't? Or how are we going to find out that it will so we can do something about it? Then you got the requirements. That's like um, like the hard things that you got to really stick to. Because that could be from your customer, from your boss, from whoever you're designing for, gives you these requirements. Okay, we got to follow those. And then we also got to verify that we followed them. And then you got industry practices, generally, if you're going to test like if your parachute will survive the ejection charge, generally you don't fire it out of the cannon. So, you got to look at like how can we test this and how can we test it in a way that like most people would do. And a good thing for this is there's like ASTM, which is like the American Standard. Do you remember the acronym? American Standard Testing Metric or something like that. And ASTM has like thousands of predefined tests that you can look up for a bunch of different tests. We use a bunch of them for both teams.
American Society for Testing and Materials.
American Society for Testing of Materials. Yeah, so they have a bunch of standardized tests that you can do for like so many different things, not just like aerospace or even like most engineers. I've seen tests that are like, what is like how to determine like the strength of your carpet from being slid off of like the floor. I think that's the craziest one I've seen. But yeah, so a lot of it is kind of like building off of what other people have already done and what standards there already are for testing.
Yeah, some other interesting, I guess, examples would be materials testing, certain sizes of the components that you put in machines, like the Instron for testing the strength of things like adhesives. as well as material of the certain like standard dog bone size for like just actually testing a material. And there's also really interesting ones for like how can you say something is waterproof or water resistant? Is something I don't know. There's also standards that are not just by ASTM, by like other things. For a really good example that Laura sent me recently was a picture of her Amazon box, and you wouldn't even know if you like looked up close, but there was like a packaging corporation stamp, and it was like this box passes this edge crushing test. Like it's everywhere. These standards are everywhere and they're for everything, not even the product that the box was holding, but like the box itself had its own set of standards. And like ways of testing. So yeah.
Exactly. Yeah. And then we've got brainstorming. So that's where you really come up with the test itself. So you look at what variables do we want to test? What materials are we going to need? What method are we going to use? And that kind of goes back to like, are you going to work with a standard? Or are you going to kind of come up with something on your own? And we need to look at how you are actually going to collect the data. In some cases, the data collection can be pretty tough. You might need to set up like an analog to digital converter, like for materials testing. You got to use the instron, and that can be a little difficult, even just to like get time with it, let alone actually like record your data right. And then you go into planning, so you can make little prototypes of what you're going to test. And then this is the part where you look at how are you going to test things safely, so that nobody gets hurt during the tests. And some of them can be some of the things that you need to test can be for pretty like extreme things, like for example, that materials testing I was talking about before. That av bay that we pulled on like totally shattered when it got pulled through. So we needed to make sure that it like wasn't gonna fly off in anyone's face or something like that. Then you'll look at number of iterations. Some tests you might just need to do more than one of. Some tests you can't really do more than one of. Like if you're looking to do like a flight test of something, like we can't afford to do 100 flight tests because motors are like super expensive. So that's something that you got to weigh in on. And then you got to look at the requirements for a pass or a fail, because of course we need to know at the end of the day, a lot of these tests are just to verify requirements. So we need to see what's a pass for this requirement, what's a fail, or for our design goals or whatever else we're looking to investigate. Then you actually execute, you go and do the test, you collect your data. And then after that, you analyze, you process the data. Some of the data that you get isn't that useful to begin with. And you need to do some post-processing. Like I know with the parachute drag tests, our data starts off as like, how far did the parachute drop? How long did it take to drop? And then we need to go from that and we need to find out what its coefficient of drag is. So we start off with data that may not be so good, and we need to post-process it a little bit, clean it up, and make it a little more useful. And then from that, we can say, does it pass or fail this requirement? If it does fail, we got to look at, well, why did it fail? Is the material too weak? Does this parachute need to be bigger? Do we need to redesign everything that we've done? Or is it just like, oh, someone set up the test wrong? And then if it turns out to be something that is an issue with the design, then you got to look into a mitigation plan. Is it something that we can quick tweak and remake? Is it something that we can't really remake because it would take too much time or it's too expensive and we need to alter what we already have? Or is it something that's like, we got to totally restart this? There's no way this is going to work. And then that brings us into results and troubleshooting. So step one is panic. No, just kidding. Step one is don't panic. Step two is analyze the data. So we'll look at the point of failure. So like materials testing, we'll look at how much force or stress did it take to fracture this material, or maybe for a parachute test, we can look at right before it hits the ground, we could look at its velocity at the ground and see, oh, that velocity is a little bit too high. And we can also look at notable trends, um, if we, for an example for this, I would think like, if we think that our epoxy has a density of maybe like, I don't know, 5 ounces per cubic inch, and then we do a bunch of epoxy tests and it's actually like 2 ounces per cubic inch, then that's kind of a trend that it's like, maybe, this isn't what we thought it was. And then you got to take your data and look for a solution. So does the failure make sense? We dropped this parachute and our velocity hitting the ground was Mach 4. Oh, wait, that doesn't really make sense. A parachute should not be going Mach 4. Not this close to the ground anyway. And then when you reason through a solution, you look at, does that solution make sense? Okay, our parachute didn't work, so we're going to use one that's big enough that you could put it on a SpaceX Dragon capsule. Oh, well, that's probably as big as the rocket. That probably doesn't make much sense. And then you look at, does the solution address the failure? If it makes sense. So our parachute didn't work. So we're going to change our epoxy. We don't like JB Weld anymore. We're switching to air epoxy. Wait a sec. What the heck does that have to do with parachutes? So it's always a little bit of a process. And sometimes you don't even go through this process once. Sometimes you go through over and over and over. Like you could get to, does the solution address the failure? And it's like, no, it doesn't really. Well, then it's like, oh, well, we kind of have to go back to the start and come up with an actually useful solution. So yeah, it's just try again, implement your solution once you have it, and then you got to repeat the test because, of course, you still need that pass fail, or I guess more specifically, you need it to pass. So you got to redo the test and see, okay, is this solution what we need, or do we need to go back to the drawing board? And then we'll go through some common tests. So for launch vehicle, we've got material strength test. So a lot of times that's for epoxy, is the big one. You could also do overall systems like the avionics bay, like I was testing, or like I was talking about. We've done a little bit in the past with fiberglass, but some of that can be a bit tough. I know one thing, last year we looked into trying to use some strain gauges on fiberglass and doing some drop tests, but I don't think we ever ended up getting to that. And you got drop resistance demonstration, that could be like, you could do it under parachute. You could do it off of like a smaller surface. So that could even be like an in-flight test pretty much. Like you could fly a rocket and have it land and be undamaged and say, okay, that proves that when we go to competition in April or June, our parachute is going to slow things down enough that it won't break on competition day. And we got the parachute drag analysis. That would be something like CFD. You could also do parachute drag test, and that would be like a drop test. Vehicle drag analysis, again, that's like CFD. Arguably, that could also be like a wind tunnel thing. I guess it kind of depends. Like I said, those 4 test names tripped me up so much. Then you got altimeter functionality test. That one's pretty straightforward. Like you just turn on the altimeter. Does it work? Yep. Okay, we're good. Then some of the more complicated ones might be the accuracy test. And that's where like you go up onto a parking garage or something, or use the vacuum decanter, or vacuum can vacuumer, whatever it's called, to like show that as the pressure drops, so that the altitude goes up. And then you've got ejection demonstrations. I think we have a video a little bit later. I think the link for it still works. And that's, putting the rocket all together, ejection charges or CO2, and just making sure it all goes well. before you send it up in the air. Then you got epoxy density inspection. And actually, I think that would be more of a test. So that you could do like pour some epoxy, figure out how much it weighs, or like you could weigh a little vessel, figure out its weight, and then put in some epoxy, let it cure, and then weigh it again and see how much its weight went up. And you got center of gravity inspection. Again, that's just like tying a rope around the rocket and hanging it and seeing where the center of gravity is. And then the big one, vehicle demonstration flight. That's where everything's inside. You got the motor in, go up to 5,000, 10,000 feet, wherever you're shooting for, and just hope it works. Or hope at least the parachutes work so you don't have to restart the whole rocket. And then for the payload, you got, again, material strength tests. Depending on what you're doing, your payload might take a good amount of force. Like I know last year, for our RC plane, we got told that we had to keep the kinetic energy like on landing like below 75 foot-pounds, which uh that's like, given that our plane was like 5 pounds, that meant that we had to go slow enough to meet that requirement that we had to like literally like stall the plane right before we landed it. So then we had to look at like, okay, this plane is basically gonna fall 10 feet to land. So how do we make sure that it's not gonna like totally break when it lands? Then you got electronic functionality demonstrations. I know the SL team is doing a lot with this year, because their whole payload is like a sensor suite. So a bunch of different sensors. They all got to record something. So of course they all got to work. And then we got software integration test. I know that's going to be huge for spaceport. They're trying to get that camera tracking software going. So they got to make sure that that software, when it's running, not only is it going to make its way to the camera, it's also going to like actually work and track the camera and track the rocket. Then battery life demonstrations. I know last year for SL, we got a little bit worried that like the battery life might run out while the plane was on the pad. So we had to make sure that the battery that we used for it could hold enough charge to keep it going up until launch and through launch. Then heat resistance demonstration. Rocket motors are a little bit hot. They're pretty hot. So anything around them, you got to make sure that it's all good to handle that heat. And then also anything inside the rocket, the inside of the rocket can get pretty hot. Like spaceport launches in New Mexico in the middle of June, and like they literally launch in a desert, so it's like 100+ degrees out there. So the rockets kind of like become ovens. So you need to make sure that like your electronics aren't going to overheat and totally like die. So then we can move on to the payload demonstration flight. Again, that's just like the vehicle demo. That's the big kahuna. That's where you launch it. You put it in the rocket, fly, and see if it works. And hopefully it does. And then, okay, so we'll take a look at ejection testing. This is my favorite test. You get to blow stuff up. Super fun. And the purpose of this one is to ensure that the vehicle will separate and allow parachutes to deploy. A lot of the NAR guys, National Association of Rocketry, like to call this taking out the laundry. So you want to make sure that your laundry gets out. So the procedure for this one is you make an ejection charge, and then you make another ejection charge. One of them is for the main parachute, one of them is for the drogue parachute. And then you attach the ejection charges to the avionics bay, because of course that's where they usually go off from, because that's where the altimeter is, and the altimeter gives the signal for them to go off. And then you have to assemble the whole vehicle. because of course you need the mass of all this so that you can make sure that the charges are enough to push the whole mass. And then you place the vehicle on a test stand. In our case, usually we use two metal chairs. It lets the rocket slide back and forth when it gets pushed by the ejection charges. And also it won't burn from like the explosion. And then you back away a little bit, of course, and then you ignite the charge. We have a little document for that somewhere in Teams. I forget where offhand. Makes sense. Yeah, Burrito is great at documenting stuff. Also, she just got engaged. Yeah. Okay, so I think we have a little video. We were very happy about this because I think this was probably like at least midnight. Ejection testings always run super late.
It was 2 a.m. when we finished.
Yeah. Yeah. And that was not even the latest we stayed for ejection charges. One time we changed the shock cord like 2 days before launch. So we had to redo ejection testing. And Harry and I stayed up till like probably like 3:30 ejection testing because we could just not get it out for some reason.
And I believe for scale testing, I think they have to change the size of one part of the airframe and they had to go back, manufacture part of it and bring it back because it wasn't large enough.
Yeah. For subscale last year, that sucked because we went to do ejection testing. Then we realized, hey, the airframe is literally not long enough for us to fit the parachute inside of it. So we had to look at, okay, we either need like a smaller parachute or we need a bigger rocket. And we decided on a bigger rocket. So we remanufactured a part of the subscale like a few days before we launched. And then we had to do the ejection testing. And of course, that went pretty late because we had to wait for the new section. So if it went wrong, what do we do? Well, a few different things. Like I said, one of them, in one case, it went wrong because we couldn't even start it because the rocket wasn't long enough. So what do is we make a new part of the rocket. And we had to be careful with that because, at least for the SL, for the subscale, the subscale has to be 75% the size of the full scale. So if we change the subscale, we're changing the full scale too. So we got to look into, if we make this change of the subscale, is it going to like totally make our rocket unstable? And thankfully it worked out well. Another thing is like the charge goes off and the rocket opens up, but the parachute doesn't get all the way out. The laundry is still in the dryer. In that case, well, maybe we just need to make the charge a little bit bigger. Or it doesn't work, but this time the charge goes off and the rocket does not even open up. Then in that case, we need to say, okay, well, we probably need a way bigger charge. And yeah, ejection testing is always just a fun test, even if it does go very, very late. It's super hands-on though, which is fun. Okay, so now we're going to take a look at my very own rocket. This is my L2. It's not actually done yet, but we'll kind of go over we'll kind of assemble the whole structure of it. It's also my L1. So it was my L1 like this. And then I'm making it a little bit longer. It's going to have a bigger motor. And this time it's going to use an altimeter to set off ejection charges versus last time the motor had its own ejection charge sort of built in. Okay, so I'll just bring it over to this table here. Anyone wants to come close and see what's going on? Let me just adjust the camera real quick. Cool. Okay, so for the L1, we just take a look at that. the L1, it just started off like this. So we had a main airframe, some fins at the back, and then we had a nose cone. And on the inside here, see if I can get that. Inside here we have my shock cord. Also, it kind of smells like fireworks. Sorry, because the ejection charge. The ejection charge, I think, smells like popcorn, but a bunch of different people think it smells good. Do you think it smells like popcorn?
Oh, yeah.
So this is my shock cord. Usually, the other end of this would tie through the eye bolt here, so that when it's separated and they're both underneath the parachute, which would be like right around here. So, or usually be like right here, pretty close to the nose cone. It would just it would keep both sections connected so that I didn't have to like look through boards.
But also enough that the two sections won't.
Yeah, exactly. Enough that the two won't collide. So usually when you tie it, you have it closer to one side than the other, because that way when it's straight down and the nose cone is kind of swinging, right now it's only hitting shock cord, and that's fine. Versus if we had it like this in the middle, then everything's under parachute. But when our nose cone swings, it hits the rocket. That's not good. We actually had a problem with that last year for SL. Two of our sections hit each other under parachute, and one of them totally broke off. It fell like 400 feet. And we had to like repair it. It was pretty bad. Okay. So then, to make it into my L2, I'm adding on these sections. And then I have a little bit extra to show for that. So a big change about L2s is that you use an altimeter to set off ejection charges. So for the L1, the motor would go into the motor tube back here. And at the forward end of the motor, you could put in a little bit of black powder so that when the motor got done burning, it could just set off the powder and eject the parachute. With the L2, though, you incorporate an altimeter because the L2 goes higher. So we need two parachutes so that we can have the drogue in the main, so that we can have a big enough parachute in the main to slow things down. But we don't get so much drift, and to avoid the drift, we use a drogue parachute. So to hold the altimeter, we've got an av bay. The av bay is inside this thing called a coupler. The coupler is this like cardboard kind of part. It's actually phenolic, which is like, it's kind of like fire-resistant cardboard you can think of. I also have this little switch band in the middle. The main thing for this switch band is to hold my P-lock switch, which arms the altimeter. Because until the altimeter gets onto the pad, or until the rocket gets onto the pad, you want to keep the altimeter like not activated. That way, you don't actually accidentally set the ejection charges off, like near people. So in my case, or I guess I'll show these parts. So this is my electronic sled. This is what the altimeter is actually going to go on. And then also AA battery will also go on here too, or not AA, a 9-volt battery will go on here to power the altimeter. And then to house the sled, I have these threaded rods that go through holes in the sled. And then those holes go through these bulkheads. Because of course, you want the ejection charges close to the altimeter so that you don't have to wire a bunch of stuff, but also setting off explosives next to your electronics is not a good idea. So you have these bulkheads to protect the half bay. So this goes in like this. Yeah. Got to bring nuts to secure this. So it's gonna be a little bit sus. Okay. But you get the idea. I'm gonna take this out so that I can actually close it to show you it looks like close. So see, this is my forward bulkhead, goes on the forward section. That's my aft bulkhead, goes on the aft section. So now it's this little capsule. And let's see, this is the aft side. So now instead of my shock cord tying into the nose cone, it'll tie into my aft eye hole, just like this. And then on the other side, my forward eye bolt I'll get a new shock cord, put it on here, and then the other end goes onto the nose cone.
Is that going over the rocket once you do the parachute stuff?
Sort of. So the way it'll be set up is take out the bulkhead the bulkhead's just this. So the ab bay or the coupler goes into both sides of the rocket. And on one side, it's designed to stay there permanently, stay connected permanently, and that's this side. And then the other side, it's designed to let the aft part break away when the explosion goes off. So the way we do that is with rivets and shear pins. I actually brought some of those that we can show. Okay. So So I've got a rivet here. This is a plastic rivet. Plastic ones are nice because they're removable, but also they're not as nice because they're really weak. But for something like this, it's totally fine. So rivets have two parts. They've got this bottom piece that goes into a hole that you want to secure. So in this case, I have 3 holes on this to kind of distribute the force a little more evenly. I have 3 holes on this just to distribute the force a little more evenly. So I put in the bottom piece. And then there's this head piece that goes in. And I'll get another rivet because that'll actually be really annoying to take out and show you this. When that head piece goes in, it makes the bottom piece kind of like flare out so that you can't pull it out. And then also, since the bottom piece is like a solid piece, you can't really move it side to side either. So you can kind of see right now, the 2 pieces, like the bottom piece is just like a straight cylinder, but then when I push it closed, the bottom piece like flares out. So now if it were inside something, I can't pull it out. I would have to remove the head first. Which in flight that wouldn't happen because there's not really any flight forces that would remove the head, as long as it's pressed in all the way. For the other side, we use these little shear pins. So I'll put in one. Let me tuck in my shock cord. So these little shear pins are basically just like little tiny screws, and they're like born to die. But basically, when the explosion goes off, the force of the explosion pushing the rocket body out puts a bunch of shear on this pin and it breaks it, and then there's nothing stopping the rocket body from coming out. So we don't want to stop the rocket body from coming out anymore. Why do we even have these in the first place? Does anyone know why? Exactly, yeah. More specifically, it's when it's like high up in the air. Because what will happen is, when you go high up enough, the atmospheric pressure gets pretty low, but the pressure in the rocket can't really like equalize fast enough. So all of a sudden you have this big pressure inside the rocket and this little pressure outside the rocket. And if you don't have shear pins, then the rocket will just like pop open too early. And if that happens when you're going like 100, 200 feet per second, then that's really bad. So this part just goes in like this. Have these marks on it to show where it's supposed to line up. And in the future, when I paint it, I use the paint to kind of guide. Okay. Stand it. I'll hold it like this. So, oh yeah, I have 2 sets of shear pin holes because I drew the first set wrong. So it just goes into one of these holes like this. And then there you go. Same thing with like, it's not really gonna come out. Also, it's gonna suck to take out later. But when an explosion goes off, this is gonna get pulled up really fast or really hard, and it's gonna shear the pin. It's gonna shear the bolt. And then we have the same thing going on for the nose cone. The nose cone goes on top. And then, you know what, I'm not gonna shoot that. Those suck to think out without an explosion at least.
This is a nose cone part, so there's like 3 different sections that are coming apart of this.
Exactly, yeah. So we'll have the nose cones one part. Nose cones one part. Dang it, I shoot. Okay. I'll kind of fix this, see if I can take that one. Probably not. But these, the av bay and this gray section that I haven't painted yet, are another section. And then this whole aft section is its own section. So usually you'll have your main parachute in your forward section, and then you'll have your drogue parachute in your aft section, at least with a dual deploy rocket. The reason for this is because generally your aft section is the sturdiest. It's like we've got a bunch of epoxy here. And overall, it's just like, it's got centering rings, it's like more reinforced to handle the launch forces. So generally, we want this to hit the ground first and take away some of the energy. So you have your main parachute like in this section and connected to the nose cone so that it's furthest away from the aft. And that means that the aft is the lowest part. Because of course, the main parachute is the highest part. And then whatever's furthest from the main parachute is going to be the lowest part. Okay, yeah, I don't even deal with it. At least not now. And then I'll point out this little part. So this gray thing here is a motor retainer. So with the motors that we use for this rocket,
What class motor do you use, please?
for the L1, I used an H class. It was an H219. For the L2, use, or at least I'm planning to use a J class motor. I think it's probably going to be a J425. But for getting certifications, you just need to use one that like that level is authorized to use. Like I used an H, but I could have used an I because level 1's going to get H's or I's. But I's are more expensive, so I didn't H. Same thing with like L2 is like J, K, or L, but L motors are like $1,000. So I'm not going to do that. So I'm just going to go with the J. What? Yeah, certs, your own thing. So for let me put the solar source in the camera. So the motor goes in this motor tube down here. And the way that it goes in is it just like pushes in, and then it kind of has like a little stop on it so that once it goes in far enough, the stop hits your centering ring. And then also when the motor's firing, that stop like transfers the thrust into this bottom centering ring, pushes everything out. The issue with that is if we're just sliding the motor in the bottom, then when it's on the launch pad, it's just gonna like fall out. That's what this little motor retainer is for. So basically what happens is the motor goes in, and then we put this little motor retainer just on top of it, and then screw it into the centering ring. And it's got a hole in the middle for the flames to come out. Mostly at least, you can kind of see it burn on oh, even more there. And really like this thing is just like a tiny piece of sheet metal. It's not really meant to carry any load. It just stops this little motor from falling.
It's only one of those rings, you know, like another one farther up.
Wait, sorry, can you repeat that?
Is it just like for just the bottom right there and not farther up?
Yeah, just the bottom here because when you push the motor in, it has a little stop, so it doesn't have it. The stop that's built into the motor stops it from going too far in, but then it's meant to just slide in. So when you first slide it in, there's nothing stopping it from just sliding back out. And when it's on the launch pad like this, gravity's going to pull the motor out.
And that's enough to literally load the entire motor home process.
Well, this doesn't actually bear the load for any thrust. It just stops the weight of the motor from like having it fall out. So, and like the motors, they're a little bit heavy, but like they're not that bad. So you just need a little thing to stop it from falling out. And then of course, once the motor's firing, like it's going to be like its own weight is nothing compared to its own thrust. So you wouldn't even need that. But then you go back to like parachute deployment. Now all of a sudden gravity's an issue because usually the fins touch first for the rockets. So you have it oriented like this. So again, the motor can just fall out. That'd be bad news because sometimes they're still a little bit on fire. And then two other little things I can point out are these things here are rail buttons. When your motor first starts firing, your rocket isn't really stable because the stability of the rocket comes with its velocity. Because the stability is kind of generated by the fins, and of course the fins can only generate force if they have drag, or they can only like produce lift, I guess, or like aerodynamic force if they have drag. So to get more drag, you need to be going faster. So when your motor first starts firing, it's a bit tough to keep it stable. So what you usually do is you put it on a rail, and then when the rail, or when your motor first starts firing, your rail stabilizes the rocket until it's going fast enough that its own aerodynamic forces can keep it stable. And then lastly, you can see these little marks that I made. On launch day, you're always going to do this. You're going to hang your rocket by a rope, and you're going to mark its center of gravity, which is this little symbol. And then your center of pressure you just get from your open rocket or whatever other simulation software you use, because there's no way that you can really just like measure that like the weight. And then you go into your software and you put these in, and you just double check that like your weight's all good, and that your rocket is still projected to be stable.
What would you do if it wasn't?
If it wasn't,
change.
yeah, the main thing that you'd probably change is the center of gravity. So if these are too close together, then you could put ballast like up by the nose cone, and ballast is just like dead weight that just changes the center of gravity. So you just put a bunch like up by the nose cone, and then that would bring your center of gravity like more forward until it's at a good spot. If it's way too far forward, then if you have ballast on the nose, you can just take that off. If you don't have ballast, then you might need to look into a redesign, or just look at some way that you can save weight and bring the center of gravity back. you just kind of try to work with what you've got. Sometimes you might even say like, oh, well, it's not ideal, but like, we still run with it. Like, I know my stability wasn't as good as my simulations on launch day, because that just kind of happens with manufacturing. Like, things don't always get built as you predict them to be built. So mine was like, my center of gravity was a little bit further forward than I thought it would be, but it wasn't that much farther forward that I had to really worry about. So I just rolled with it. So that'll be it for today. I have not. I'm planning to launch it on the 12th. But we'll see if that happens. We'll see if I get it done in time, and we'll see if the launch field is even open after this hurricane. So it's planning to do Palm Bay, and the whole hurricane's kind of like cutting across Florida. So okay, just looking in the future, hoping to do structures on Tuesday, but room reservations always are a little tricky with these hurricanes. So room might get changed, time might get changed. Just keep an eye on Slack. And we're going to use Fusion 360 and do a little demo. So again, we got Slack, Insta, all that. Any questions? Yes.
Do you need a code for Fusion 360?
There's a way that you can just like sign in to Autodesk, which is like Fusion's company. Yeah, you just sign in with like your UF email, and then you can like download like a student copy, which is basically a full copy. It's a pretty good deal. Okay. Any other questions?
How can I join the teams?
Oh, we've got that link right there. You can go ahead and go to that link and then join from there.
For what?
For the teams.
Yeah.
Go ahead and DM me on Slack with your UF email. I'm Reed McAdam. And then I can add you from there. Yep. Okay, that's it for today. Thank you for coming.